Hello, everyone. My name is Idris, and together with Guabina, we're going to talk about one of the problems of our molecular thermodynamic of fluid phase equilibria book by Prausnitz. So this is a problem at the end of chapter 6, problem 18. And it states that there is a binary mixture of nonpolar components at 25 degrees Celsius, and it basically asks us to find at what compositions are these two components miscible. And the only data we have is the infinite activity coefficients of component 1 and component 2, which are given here. So Kwabena is going to start the solution of this problem.
Okay, thank you, Idris. My name is Kwabena, and I'm going to take you guys through part of the solution, and my partner Idris will continue with the rest. Okay, so in order to obtain an unstable region at constant temperature of the Gibbs energy with respect to the mole fraction of one of the components. So in this case, we are using the first component, that's component 1. So we have X1 at constant temperature and pressure plus the product of the gas constant and the temperature in Kelvin times the inverses of the sum of the mole fraction of the two components, 1 over X1 plus 1 over X2. So all these expressions should be less than 0. Okay, so again, we use the Redlich crystal expansion. We truncated it at the second expansion to 2 parameter. So we have this equation, the equation 679, where we have the Gibbs energy divided by the product of the gas constant and the temperature being equal to the product of the two mole fractions that we have, X1, X2, times the expression, the A prime plus B prime times X1 minus X2, where A prime and B prime are empirical constants and they are all temperature dependent parameters. And these parameters must be obtained or determined from experimental data. So again, we use the Redlich crystal expansion equation and we obtain equation 680 and 681. So in order to obtain infinite dilution. So the first one, we assume that our X1 is equal to 0. If X1 is equal to 0, definitely X2 is equal to 0 because a fraction, we have two binary mixture. X1 plus S2 should be equal to 1. If X1 is 0, S2 is equal to what? 1. We make our substitution, then we obtain this equation at infinite dilution. So we have the infinite activity coefficient of the first one being equal to A prime minus B prime. Then with the second one, we assume that our X1 is 0 and X2 is equal to what? 1. We make our solutions, and in order to, our X1 is equal to 1 and X2 is equal to 0. We make our substitution to obtain the ln or natural log of the infinite coefficient of the second component being equal to A prime plus B prime. In the problem statement, we were given the infinite activity coefficient of the two components to be 9.3 and 4.7 respectively. We make our substitution to obtain 2.23 being equal to A prime minus B prime and 1.55 being equal to A prime plus B prime. We solve these two equations simultaneously to obtain values of A prime being equal to 1.89 and B prime being equal to minus 0.34. We further make substitution. So we substituted the values of A prime and B prime into the two parameter expansion of the Redlich crystal equation. So we make to obtain the equation that we have now. So we know that x1 plus s2 is equal to 1. Let's make s2 the subject. We get s2 being equal to 1 minus x1. We substitute this value into the above equation to obtain the equation, which is the Gibbs energy written in terms of x1. Idris will continue with the rest.
Thank you, Kobina. So now that we have the expression of Gibbs free energy based on the molar composition of our component 1, we can take the derivative of the first derivative of Gibbs free energy based on the molar composition of component 1, and this is what we get. And after we take the second derivative, we get the next equation. So now we can substitute that in our instability equation, and this is what we get after the substitution. So in order to this equation to be valid, we know that RT cannot be negative. So this part in the parentheses should be negative. And in order to find what is the range of x1 that makes this equation negative, we need to find the roots of the equation in the parentheses. And so when we rewrite this equation, we get a third order polynomial. And when we solve for the roots, we get 3 different values for x1, which they are 0.352, 0.421, and 1.653. So we know that this could not be our answer because the value of x1 should be between 0 and 1. So we discard this one. And now, in order to the instability to happen, we know that the value of x1 should be between 0.352 and 0.421. Thank you, everyone, for your attention. I hope you guys have a good time.